All right, everybody, welcome to the video here for our independent study for Unit 1. So in this video, we're going to go through what are called polynomial identities. I'm hoping you already started kind of reading through this a little bit before watching the video, or if you're just looking at this for the first time. To understand what an identity is in algebra, all we really have to understand is that it is a true equation for all variables in the equation. So I gave you an example here for an identity that you actually kind of already know about or have probably seen before, either in Algebra 1 or throughout this unit of factoring in Unit 1. So we know how to factor using difference of two squares. We know that x squared minus 9 is the same thing as x plus 3 and x minus 3. Now, why do we know that that's true is because of the identity that's right here below. So why is this an identity? So this is an identity because this is true for any value of a or b. If I was to randomly pick numbers and plug them in, it would be true. But how do we prove that? So to prove an identity, all we have to do is use our algebra skills to make it so that both sides of the equation simplify to the same exact expression. Now, this is a pretty easy one, because I could take an expression like a plus b times a minus b and just quickly multiply it out. I'll use some boxes here. So we have a plus b and we have a minus b. A times a is a squared. A times b is ab. We like alphabetical there. A times negative b is negative ab. And b times negative b is negative b squared. So when we start combining like terms, we see that this becomes 0ab. So essentially this whole expression becomes a squared minus b squared. So because I've taken this right-hand side of the equation and shown that it's the same as the left hand, I can now say that this is an identity. Meaning for any values of a or b, whether that's a variable like x or a number like 3, I can replace those a's and b's and it will be a true statement. So let's try a couple of identities here together and see how we do with this concept. So here's another one. So the question asks us to justify that the following equation is an identity. Since it's saying justify, it's pretty much telling us it is going to be an identity. We just have to manipulate or use our math skills to see that they're the same. So let's start on the left-hand side here. So this looks a little funny in the middle, but this is just the distributive property, just looks backwards. So I can rewrite that left side as x squared plus ax plus bx, because x times a is ax, x times b is bx, plus ab. On the other side, I have a binomial times a binomial, so again, I'll use some boxes to help me out. We have ab, not ab, sorry, xa, and xb. X times x is x squared. X times a, again, we like alphabetical there, so ax. X times b is bx, and a times b is just ab. So we could say this is equal to x squared plus ax plus bx plus ab. Notice these are the same, so this is an identity. That's it. Now, again, kind of an easy one. There are some more challenging ones, which we'll see. So on the bottom of the first page there's a note. It says if a problem asks you to show or justify an equation as an identity, we're going to assume that it is an identity, like the one that we just saw. If you're asked to determine if it is an identity or not, be careful, because sometimes it might actually not be one. That tends to come up in multiple choice questions, which you'll see later on in this video. All right, so let's try another one. This one's a little bit more challenging. So we see a bunch of different things here that can be simplified. So again, let's just start on one side of the equation. So if I start over here on the left, we have x squared times y squared and x squared and y squared. X squared times x squared is x to the fourth. Remember, when you multiply, you add exponents. Y squared times x squared, we have x squared y squared. Should have made my box a little bit bigger, but that's okay. and we'll get another x squared, y squared there. And then when we multiply y squared times y squared, we get y to the fourth. So this whole left-hand side can be simplified to x to the fourth. These are like terms, and there's two of them. So we have plus 2x squared y squared, plus another term there of y to the fourth. On the other side, we have another binomial that's being squared, so we need another box set up here. Now this time it's the same terms but subtraction, so just watch your signs here. So we should get the same stuff, just I'm going to have negatives in places, right? Use the problem you just did. All right, so when we multiply a positive and a negative, it becomes negative. So these two boxes wind up becoming both negatives. And when we multiply a negative y squared and a negative y squared, we should get a positive y to the fourth. So again, those are like terms, so those are going to combine out together. So we get x to the fourth minus 2x squared y squared plus y to the fourth. But notice we haven't done anything with this yet. So this is not a binomial, this is a monomial that we're squaring. So essentially that squaring is happening to all parts of that. Easier way to think about it is it's being multiplied to itself. So I have 2xy times 2xy. So 2 times 2 is 4. X times x is x squared. And y times y is y squared. So right now these don't look the same, but I can still simplify on the right-hand side here. So if I look, I have a like term here, and I have a like term here. So if I add those two together, I get x to the fourth. A negative 2 and a positive 4 would give me 2x squared y squareds. And then another y to the fourth. And then we can see that this actually is an identity. So because we now have an identity, I can say this is true for all values of x or y. So we can say yes, the equation is an identity. Now this identity is kind of a unique one, right? If you plug in values of x and y as numerical numbers, you'll notice something. So go ahead, pause the video for a second, and if you haven't done so yet, try and plug in 3 and 2 into that original expression and see if you notice something. All right, so if you tried this, you probably noticed something happened here. So when we plug in our x, we would have 3 squared, plus if we plug in our y, we would get 2 squared. And on the other side, we would get 3 squared minus 2 squared. And then we would have plus 2 times 3 times 2 squared. Well, over here, we're going to get 9 plus 4, which is 13, so we'd have 13 squared. Over here, we'd get 9 minus 4, which is 5, so we'd get 5 squared. And over here, we would get 12, so we'd have 12 squared. Well, 5, 12, 13 is actually something that we call a Pythagorean triple, because this looks just like the Pythagorean theorem. So this identity actually helps us find some of the Pythagorean triples that are numbers that work for the Pythagorean theorem. Just a little interesting little factoid. All right, so let's try another one. So here's another expression, and we're determining whether or not it is an identity. So again, it doesn't say to prove it's an identity, it's asking us to determine whether it's an identity. So we're going to assume that it might or might not be. So it could go kind of either way here. So if we start multiplying this out, let's see what happens. So we have a binomial times a binomial. So we have 2a squared, we have b cubed, we have another 2a squared, and we have a negative b cubed. So this is going to come out to be 4a to the fourth. Already I'm not seeing things I like. We have a 2a squared b to the third, Remember, we like alphabetical order for the variables. Over here we have a negative, so it's going to be a negative 2, because a positive times a negative makes a negative. And then another a squared b to the third. These I could already see add up to 0, right, like terms. And the last box should be a negative, because it's a positive times a negative, and we'd get b to the sixth. So this whole left-hand side comes out to be 4a to the fourth minus b to the sixth, which is not equal to 4a squared minus b to the third. So we can say the equation is not an identity. All right, so identities do pop up at times on the Regents exam, and when they do, they're either multiple choice or free response. Most of the time we see them as multiple choice questions, and a lot of them look like this, where they give you 3 different equations or more than 3 different equations, and they ask you which of them is true or not true. Notice it doesn't actually say the word identity in this problem, but it's asking you about an identity concept, right, or the identity concept. So let's just take them piece by piece, right? There's always at least a couple multiple choice questions which require you to do just a lot of algebra to be able to get the answer. This just so happened to be one of them on this particular test. So if we look at the first option, I can take that that left-hand side and multiply it out. So if I take m plus p and m plus p, we should have m times m, which is m squared, MP and MP, and P squared. So we could see that the MPs are like terms, so I have 2 MPs. So that whole thing is going to be equivalent to M squared plus 2MP plus P squared, which is what it says, so this one is true. That is an identity. All right, let's take a look at the second one. So for the second one, we have x plus y to the third. So really, when we have something to the third, it's saying x plus y times x plus y times x plus y. We can only multiply 2 things at a time, so let's multiply 2 x plus y's first. X plus y, x plus y. So x times x is x squared. We have xy, xy, and we have y squared. So that whole thing is going to become x squared plus, again, like terms, so we have 2xy. So we have 2xy plus y squared. Now this is only going to be the product of xy times xy, x plus y, sorry. We have to multiply another x plus y to this expression. So I need to make another set of boxes here. So we have x squared, 2xy, and we have y squared. And we have to multiply another x plus y. So we have x squared times x, which should be x to the third. We have 2xy times x, which would be 2x squared y's. We have an x and a y squared. X squared and y becomes x squared y. We have like terms there, so that would be 3x squared y. We have 2xy times y, so that would be 2xy squared. So that's going to give us 3xy squareds. And we have y squared times y, which is y cubed. So the whole expression of x plus y to the third power is going to become x to the third plus 3x squared y plus 3xy squared plus y cubed. So we could see that's not what they have here, so this one is not an identity. So right away we know that it's not choice 2 or choice 3 because it asks us to figure out which ones can be proved for all, and we know that 2 doesn't work. So now we're left with that last one. Luckily, that last one we kind of just did, right? So if you look above that Pythagorean theorem one we did, well, that's the same thing, just instead of x's and y's, they put a's and b's there. So we could do it again. It's the same steps again. So we're going to play with this left-hand side here a little bit. So we have a squared, b squared, and a squared, b squared. So we're going to get a to the fourth. We're going to get a squared b squared twice, meaning we're going to have two a squared b squareds. And we're going to have a b to the fourth. So that's the whole left-hand side is going to become a to the fourth plus 2a squared b squared plus b to the fourth. Well, now we have to tack this side. So a squared minus b squared squared, right? Again, it's just a lot of algebra, not algebra that we can't do. Watch our signs. So we'll have a to the fourth, we'll have minus a squared b squared, we'll have minus a squared b squared, and we'll have a positive b to the fourth. So that's going to become a to the fourth minus 2a squared b squareds plus a b to the fourth. But then remember, we have to deal with this, so we're squaring something. So 2 times 2 is 4, a times a is a squared, and b times b is b squared. And then just like before, we have like terms here and here. So this one is actually going to be true as well, because when I combine those like terms, I'm going to get 2a squared b squareds. So 1 and 3 both work, giving us choice 4. The last question on this video shows us a algebraically prove. So they're telling us to algebraically prove. They're telling us to prove that this is an identity. So that tells us it is an identity. So this is going to be true in some way, shape, or form. To be able to do this question, we have to work on our algebra skills. We could do this a lot of different ways, and I'm actually going to show you 2 right now. Just know that this has to be here to make sure that it is a valid equation. If x was -2, then this would be undefined. So don't worry about that. We're not plugging in -2, it would just make everything undefined, which would be irrelevant. So we're just playing with the algebra here. So, like I said, 2 ways. So the first way we're going to talk about is using the method of inspection. So if I look at this left-hand side, the numerator looks to be bigger than the denominator because 9 and 8 are different. So I'm going to rewrite the numerator so that I can possibly reduce this. So I'm going to say x cubed plus 8 plus 1 all over x cubed plus 8. Now, why am I doing that? Well, because this denominator is being shared between all of the parts in the numerator, I can actually rewrite this in 2 pieces or 2 fractions. So I can say I have a fraction of x cubed plus 8 over x cubed plus 8 plus another fraction of 1 over x cubed plus 8. Right, if I have like terms, I would add these together, or like denominators, I'd add these together. I'd get back to 8 plus 1, which is really 9. So I'm kind of undoing the combining of fractions here. Well, the reason why I did that, because I looked at it and I said, well, if I could reduce this whole thing, I can make that a 1. Therefore, it's the same as the other side, so this is an identity. Now, the method of inspection is great, and some of us are like, that's easy, that's how I would do it, and some of us are saying, I would never think to do that. So if you're one of those people that would never think to do that, I would probably go on the route of making a common denominator on the other side. So on the other side, I have 1. Well, 1 means it could be anything divided by itself, and if I want a common denominator, I want to make the common denominator x cubed plus 8. So if I want to make this 1, I need to put the same expression divided by the same expression. Well, then if I combine my like terms here, because these are like terms, they have a common denominator, I would get x cubed plus 8 plus 1 all over x cubed plus 8. And then I can see that that becomes x cubed plus 9 over x cubed plus 8, because I can add together 8 and 1. And that's the same as x cubed plus 9 over x cubed plus 8. So we are done. We've algebraically proven that this is an identity. Hopefully this video helped and you understand the idea of identities in algebra. Good luck.